Today we are going to discuss about conductometric titrations. In conductometric titration, we measure conductance as a function of volume of the titrant. We draw a graph between conductance and volume of the titrant. For example, for strong acid, strong base, we get a graph like this. This point of inflection is the end point of the titration. When do we use conductometric titration? Whenever you don't find a suitable indicator for a titration, whenever the color change at the end point is not distinct, then we cannot find out clearly the difference between the color before the end point and after the end point. Whenever you don't find a suitable volumetric method, for example, for weak acid, weak base titration, for precipitation titrations, it is when you don't find a suitable indicator to perform a titration, when the color change at the end point is not distinct, when there is no suitable volumetric method, and in titrations like precipitation titrations where it is difficult with the available indicators. Under these circumstances, we make use of conductometric titrations. We can use conductometric titrations for various types of titration. We will first take up the case of strong acid, strong base titration. For example, if you use hydrochloric acid as a strong acid and sodium hydroxide as a strong base and perform a titration conductometrically, what we will get is NaCl, sodium chloride and water as a result of this neutralization reaction. Instead of HCl, we can make use of other strong acids like sulfuric acid, nitric acid, etc. Instead of sodium hydroxide, you can make use of potassium hydroxide, etc. Here, HCl is strong, sodium hydroxide is also strong, sodium chloride is also strong. When you say a particular electrolyte is strong, what we mean is that it has got completely dissociated, 100% dissociated. Now, here, during this titration, let us assume that we take the sodium hydroxide in the burette and the hydrochloric acid in the beaker. We will put a conductance cell into the hydrochloric acid and connect it with the conductance bridge. The solution in the beaker contains hydrochloric acid, which is completely dissociated, and so we show it as H plus and Cl minus in our discussion. We will not find just 4 molecules of H plus Cl minus. Instead of that, we will find crores and crores of HCl molecule. When you add the first molecule of NaOH into the beaker containing hydrochloric acid, NaOH and hydrochloric acid will react to form sodium chloride. If we look at this, hydrochloric acid in the beaker is replaced by sodium chloride. When H plus is replaced by Na plus, we will see what happens. H plus is a lighter ion, its atomic weight is 1. Atomic weight of hydrogen is 1. That is in fact the lightest atom available. Whereas for sodium the atomic weight is 23. That means sodium is 23 times heavier than hydrogen. So H plus ion is much lighter. If you say it is lighter, then it goes without saying that the lighter ion will move faster. Na plus is heavier. That means The heavier ion will move slower. So the faster H plus ion is replaced by slower sodium ion. Because the speed of the ion decreases, conductance also decreases. Conductance is directly proportional to speed of ion. When the H plus ion is replaced by Na plus ion, the lighter ion is replaced by heavier ion, and so the speed of the ion decreases. When the speed of the ion decreases, the conductance will also decrease. And so if we draw the graph between conductance in the y-axis, the unit is mho, and volume of the titrant, volume of the Burette solution. The Burette solution in this case is sodium hydroxide. If you take the volume of sodium hydroxide in ml, what we find is that when you add sodium hydroxide to HCl, HCl becomes NaCl, H plus is replaced by Na plus, lighter ion is replaced by heavier ion, that is, the speed of the ion decreases and the conductance decreases. So what you will get is a decrease in conductance. As you continue with the titration further, as you add more and more sodium hydroxide to HCl, all the H plus ions will be replaced in turn by Na plus ion, and Na plus ion being the slower ion, the conductance will decrease. What you find here is that the faster ion, fast H plus, is replaced by slower Na plus, and so the conductance decreases. We don't find any more HCl in the beaker, the paints. That is the end point of the reaction. Say HCl has completely reacted with sodium hydroxide. If you continue the titration, you further add sodium hydroxide. The excess of sodium hydroxide added will completely dissociate because it is a strong electrolyte, and the number of ions will increase, and the number of ions is directly proportional to conductance. So what you find is that conductance is also directly proportional to number of ions. That means the number of ions increases, the conductance will increase. Here, when you add excess NaOH beyond endpoint, the number of ions increases, and so the conductance will increase. This point of inflection will give you the endpoint of a strong acid, strong base titration. The increase in conductance is due to the excess of the strong base, sodium hydroxide, which is completely dissociated. The number of ions increases, and so the conductance increases. This is the shape of the graph which you get for strong acid, strong base titration. The second titration is weak acid, strong base titration. Example for weak acid, strong base titration is the titration between acetic acid and sodium hydroxide. Acetic acid is the weak acid and sodium hydroxide is the strong base. They react together to form sodium acetate, which is the salt of acetic acid. Salt of a weak acid is always strong along with water. Now if we take an illustration, the burette is filled with sodium hydroxide, the base, by convention. In the beaker we take acetic acid, which is a weak acid. For illustration we take just 4 molecules of acetic acid. When you add sodium hydroxide into the acetic acid, sodium hydroxide reacts with acetic acid to form sodium acetate. The weak acetic acid is converted into strong sodium acetate. When you say weak, it is not completely dissociated, it is partially dissociated. The number of ions will be less, and because you have less number of ions, the conductance will also be less. During titration, acetic acid is converted into sodium acetate. The salt of uric acid is strong, that means it undergoes complete dissociation, and so the number of ions is more. Since the number of ions increases, conductance will also increase. Now we will represent what we have seen in this illustration. Acetic acid is converted to sodium acetate. Acetic acid is weak, whereas sodium acetate is strong, and so the number of ions increases as I continue with the titration. All the acetic acid molecules will react and they will get converted to strong sodium acetate. If we draw a graph between conductance in the y-axis and volume of the Burette solution, which is sodium hydroxide in the x-axis, what we find is that weaker acetic acid is converted to stronger sodium acetate, and so the number of ions increases and conductance increases. Now all the acetic acid has reacted, and whatever sodium hydroxide you add in excess will remain as sodium and hydroxide ion because it is a strong base. And as you add more and more sodium hydroxide, the number of ions will increase and conductance will increase further, but the slope will be different. The initial increase is due to conversion of acetic acid, which is weak, W indicates weak, into sodium acetate, which is strong, S indicates strong. There is a change in the slope of the straight line at the end point. This is the end point. And beyond the end point, we find the conductance further increases because of excess of the strong base Na plus OH minus, which completely dissociates. And this is the graph which you get for a weak acid strong base titration. Now we come to strong acid weak base titration. We'll take the example for strong acid as HCl. Again, very well take sulfuric acid or nitric acid also. And we'll take the example for weak base as ammonium hydroxide. We can take the weak base like sodium carbonate and borax also. When they react together, we get the products as ammonium chloride and water. Hydrochloric acid is strong, ammonium hydroxide is weak, ammonium chloride is also strong. Remember, this ammonium chloride is the salt of ammonium hydroxide. So the salt of a weak acid or the salt of the weak base is always strong. Now we'll take the illustration where you take the ammonium hydroxide in the burette. The acid, that is the hydrochloric acid, in the beaker. During the titration, when you add the first molecule of ammonium hydroxide to HCl, the beaker solution, that is the hydrochloric acid, is converted to ammonium chloride. Hydrochloric acid is strong, ammonium chloride is strong, and so both are completely dissociated, and so there will not be any change in the number of ions. Instead of that, what you find is that H plus in Cl is replaced by NH4 plus. H plus is lighter and so it is faster. NH4 plus is heavier and it is slower. Because the faster H plus ions are replaced by the slower NH4 plus ions, the speed will decrease and the conductance will also decrease. That is, you take conductance in the y-axis and volume of the base. Here the base is ammonium hydroxide. What we find is that instead of H plus, you get NH4 plus. HCl becomes ammonium chloride and the speed of the ions decreases and conductance decreases. That is, instead of H plus, you find NH4 plus. If you continue the titration, all the H plus ions will be replaced by NH4 plus ions, which are heavier and slower, and so the conductance decreases. Now there is no more HCl to react. That means the end point is reached, and if you add further ammonium hydroxide, the ammonium hydroxide will remain in excess because there is no hydrofluoric acid to react. But there is a difference. When you take sodium hydroxide, this is a strong base and it completely dissociates. Whereas if you take ammonium hydroxide, it is a weak base. And since it is a weak base, the dissociation will be partial. Dissociation is very less, so less, something like this. Out of 1 lakh ammonium hydroxide molecules, just 1 molecule will dissociate. So if you find 1 lakh ammonium hydroxide molecules in the undissociated state, you will find only 1 molecule in the dissociated states, and so the number of ions, even when you add excess ammonium hydroxide, will not increase sharply and it will be almost constant. Pointed with the slope changes, that will give the end point for the strong acid weak base titration. And if you write the reason for the change in the slope in the graph itself, you will find first the conductance decreases because fast H plus ions are replaced by slow NH4 plus ions. After that, after the end point, the graph remains almost constant. This is because of excess ammonium hydroxide molecules present. This is a weak base. Being a weak base, it will not dissociate much, and so there will not be a very great increase in the number of ions and hence the conductance. Now we will move to the next titration, namely the weak acid weak base titration. Example for weak acid we will take as acetic acid. Instead of that you can use any organic acid, say formic acid or oxalic acid, etc. And consider the reaction with weak base. For example, ammonium hydroxide. We will get the products as ammonium acetate and water. Acetic acid is a weak acid. Ammonium hydroxide is a weak base. Ammonium acetate is salt of the weak base. Salt of the weak base is strong. Now we will take the illustration in which we will take the weak base ammonium hydroxide in the burette and acetic acid in the beaker. We will just take 4 molecules of acetic acid for example. When you add the first molecule of ammonium hydroxide to acetic acid taken in the beaker, it reacts to form ammonium acetate. Acetic acid is converted to ammonium acetate. Acetic acid is weak, whereas the salt of the weak acid is strong. So a weak acetic acid is converted to strong ammonium acetate, and so the number of ions increases and the conductance increases. We take the conductance in the y-axis, volume of ammonium hydroxide in the x-axis, and when you add ammonium hydroxide to acetic acid, it is converted to ammonium acetate, which is strong. Acetic acid undergoes partial dissociation, whereas ammonium acetate undergoes complete dissociation, and so there will be an increase in number of ions, and so there will be an increase in conductance. Now we will show this like this. When you add the first molecule of ammonium hydroxide to acetic acid, it is converted to ammonium acetate, which is a strong electrolyte. Number of ions increases and conductance increases. If you continue with the titration, all the acetic acid molecules will react to form ammonium acetate. This marks the end point of the reaction. And if you continue adding ammonium hydroxide beyond the end point, it will remain as excess. But ammonium hydroxide is a weak base. The dissociation is partial and the dissociation is very less. Out of about 1 lakh ammonium hydroxide molecules, only one molecule would have dissociated. There is no significant increase in the number of ions, and so the conductance will almost remain constant. The initial increase is due to conversion of weak acetic acid to strong ammonium acetate. The constancy up to the end point is due to the excess weak base, and so there is no significant increase in the number of ions. The point with the slope changes, which corresponds to end point. Next we come to the titration of mixture of acids with strong base. We will take a mixture of strong acid and a weak acid versus strong base, sodium hydroxide. Let us illustrate with a burette containing the base sodium hydroxide and the beaker containing the mixture of acids, namely the strong acid HCl and the weak acid acetic acid. When you add the first molecule of sodium hydroxide, it will react with the acid that is completely dissociated, which leads to more number of ions. Hydrochloric acid is a strong acid which completely dissociates and leads to more number of ions, and so the initial reaction will be between HCl and sodium hydroxide, resulting in the formation of sodium chloride, and hydrochloric acid is a strong acid, sodium hydroxide is a strong base, sodium chloride is also strong. What we find is that HCl is converted into sodium chloride. Both are strong, and during this conversion there will not be change in number of ions, but what we find is that the faster H plus ions are replaced by slower, heavier sodium ions, and so the conductance decreases because the speed of the ion decreases. We draw a graph between conductance in the y-axis and volume of the Buret solution, sodium hydroxide. Initially we find that hydrochloric acid becomes sodium chloride. The lighter H plus replaced by heavier sodium ions. The faster H plus replaced by slower sodium ions, and so the conductance decreases. If we represent it in this illustration, instead of H plus we get an Na plus, and so the conductance decreases. If you continue with the titration further, all the hydrochloric acid molecules will react and all of them will get converted to sodium ions. This will be an endpoint for strong acid because we don't find any more S here. And beyond that, if you add sodium hydroxide, the sodium hydroxide will react with acetic acid, which is a weak acid, resulting in the formation of sodium acetate and water. Acetic acid is a weak acid. Sodium hydroxide is strong base. Sodium acetate is a salt of acetic acid. Salt of any weak acid is strong. And so what we will find is, instead of acetic acid, we will find sodium acetate. It is a strong electrolyte and is completely dissociated. Since the weak acetic acid is converted into strong sodium acetate, the dissociation increases, number of ions increases, and conductance will also increase. As you add more of sodium hydroxide, the remaining acetic acid molecules will also react, and the weak acetic acid is converted into strong sodium acetate, and the dissociation increases, number of ions increases, and conductance also increases. All the acetic acid has already reacted and the endpoint is reached, and if you add more of sodium hydroxide, which is a strong electrolyte, it will remain unreacted, and so there will be an increase in number of ions and conductance will increase further, but with a different slope. The first change in slope corresponds to V1, which is the endpoint for hydrochloric acid. The second change in slope corresponds to V2, which is the endpoint for the mixture of acids. In the graph, the first endpoint corresponds to the endpoint for strong acid, that is this here. Second endpoint corresponds to mixture of acids, and so if you take the difference V2 minus V1, that should correspond to the endpoint for acetic acid. Now we will mark the reasons for the changes in slopes which we have already discussed. The slope further first decreases because the faster H plus is replaced by slower Na plus. The next change in slope is due to conversion of the weaker acetic acid to stronger sodium acetate. That is, acetic acid which is weak is converted to sodium acetate which is strong, and so there will be an increase in number of ions and increase in conductance. Further increase beyond the endpoint for the mixture of acids is due to excess of sodium hydroxide which is a strong electrolyte, and so the number of ions increases further. Now we will come to an example for a precipitation titration. We will take the reaction between silver nitrate and potassium chloride. Silver nitrate is taken in the burette and potassium chloride is taken in the beaker. When you add silver nitrate to KCl, you will get silver chloride, which is a precipitate because it is insoluble in water, and potassium nitrate. Silver nitrate is soluble in water, potassium chloride is soluble in water, but silver chloride is insoluble. It settles down as a precipitate, and KNO3 is also soluble. What we find is that the potassium chloride in the beaker is converted to potassium nitrate, and during this process the Cl minus is replaced by NO3 minus. Cl has an atomic weight of 35.5, whereas for NO3 minus, if you calculate in terms of atomic masses, this will be 14 plus 3 into 16. The atomic mass of oxygen is 16 and there are 3 atoms. 3 into 16 is 48 and you find 62. But for chlorine, the atomic mass is 35.5. And we find that NO3 minus is heavier than chloride. Since it is heavier, it is slower, the speed of the ion will decrease and the conductance will also decrease. And when you continue the reaction, when you add more and more silver nitrate to the potassium chloride, the potassium chloride will react further and all the chloride ions will be replaced by NO3 minus ions. The first ions are replaced by the slower ions, and so the conductance decreases further. And in the x-axis you take the volume of the burette solution, which is silver nitrate. We find that the conductance decreases. All the potassium chloride has reacted, and if you add silver nitrate further, silver nitrate being a strong electrolyte is completely dissociated and the number of ions increases further because there you don't find any potassium chloride to react. The excess silver nitrate will remain as such, and so the number of ions increases and conductance increases. The point corresponding to the change of slope will be the end point for this titration. Now we will mark the various regions. First, the conductance decreases due to replacement of fast Cl minus by slow NO3 minus. That is what you find here. Cl minus replaced by NO3 minus. Beyond the end point, the conductance increases because of the presence of excess silver nitrate, which is a strong electrolyte which undergoes complete dissociation, and so the number of ions increases. Now we will summarize the various graphs we have obtained. First is strong acid, strong base. For this we will get a graph like this. in all the graphs we find the conductance in the y-axis and volume of the burette solution. For weak acid, strong base, you get a graph like this. We have already seen the various reasons. For strong acid, weak base, if you plot the conductance of the y-axis and volume of the weak base in the x-axis, first the conductance decreases and after that it remains constant due to the presence of excess weak base. If you take the case of weak acid, weak base titration, you take the volume of the weak base in the x-axis, conductance in the y-axis. Because the acetic acid is converted to ammonium acetate which is strong, the conductance increases, number of ions increases with dissociation. And after that it remains almost constant due to excess of weak base. If you take the case of mixture of acids, you get a graph like this. First the conductance decreases due to replacement of fast H plus by slow Na+. It increases due to conversion of weak acetic acid into strong sodium acetate. It further increases due to presence of excess sodium hydroxide. You find a graph like this, and this is similar to strong acid, strong base, but the reason is different. Having discussed about these 6 situations, now we will summarize the reasons for the change in the conductance. Conductance is directly proportional to number of ions. When number of ions increases, conductance increases. When a weak electrolyte is converted to strong electrolyte, partial dissociation becomes complete dissociation. The number of ions increases. And the number of ions increases and the conductance also increases. So this will be lower conductance and this will be higher conductance. Conductance is also directly proportional to the speed of the ions. When the ion becomes heavier the ion, slower the ion, and conductance will decrease further. So H plus is the lightest ion, and when it is replaced by sodium ion which is heavier, it becomes slower and the conductance drops. And based on these factors which are shown here, we can explain the shape of all the scenarios. Thank you.